Can you see my screen now, the presentation?
Yes, sir. Yes, sir. Go ahead.
Okay, good. So let's start. So we jump right into it. So why do we want to measure contact motion? Yeah, there are several reasons for that, and one is to apply to standards. I will come to that later. Another is to obtain important information about the circuit breaker and the condition of the circuit breaker as maybe a part of the maintenance program or a maintenance strategy, and collect data for future trending analysis. And that is something you do preferably in the beginning at the commissioning, so you have something to compare with and to see, to trend against. Maybe the most important thing is to discover potential problems at an early stage in order to prevent serious damage. So talk a little bit about the parameters that you can derive from the contact motion measurement. So there are different parameters. I'm just mention some of them here. Stroke length, the velocity, contact velocity, closing and open speed, contact penetration, it's named wiping sometimes, and that is made also in combination with contact timing to obtain. I will explain all these parameters later. Arc and contact length in combination with dynamic contact resistance measurement, and we have also damping characteristics, which can be defined in different ways. So, and the problems that can be really revealed with contact motion measurement. Actually, is my screen switching now or not?
Actually, it's not switching, sir. Sorry.
Okay.
I don't know. Yeah.
So I'm a little bit confused here because, let's see again. It was working before. Sorry for this. I need to see the screen too. It's not coming along.
Try again, sir. We can see the front page.
Yeah. No,
yeah,
now I think.
Yep.
But now it's strange because I can't. I see only. Okay, we will try in that way. For me, it's a little bit strange because I need to look at another screen now. Perhaps. So we try this. No? Oh,
You mean it's switching, sir? No, it's not switching, sir.
it's not switching. Something is wrong here with, and when we tested before, it was working. I'm very, very sorry.
Sorry, sir. Yeah, you can fix it.
Okay, now it's, can you see the second
Yes,
screen
sir.
now?
Yes.
Okay.
Yes.
Now it seems to be okay.
Yep.
Okay, I already talked about this screen. And here now on. Okay, I need to look at my second screen. So that, okay, this was also finished. So what kind of problems can you reveal with contact motion measurement? Yeah, of course, since you're measuring stroke, you can see incorrect stroke. You can see if the close or open velocity differs from your reference values or from the specified values from the manufacturer. And that could be due to wrong adjustment or other problems like springs, lubrication pressure, etc. And another thing you can reveal is excessive arcing contact wear, lack of close and open damping. That's a very serious thing with a circuit breaker that can make a big damage, mechanical damage, if it continues and get worse and worse. Another thing is too early damping, which will cause that the velocity in the arcing zone becomes too low, and then the conditions to extinguish the arc is not according to what the manufacturer specifies. There could be also a problem with rebouncing contacts at both close and open, and which can cause then at opening restrike of the arc. It can also lead to exploded breaker in that case, because when you have this situation, there is no energy left to extinguish the arc if the breaker is already open. I will explain a little bit in the graph later. And other anomalies in the motion curve shape. So here we have the, oh, I cannot point because it's on the second screen. This. Okay. I have to try to get this working because I need the pointer. Now you see the pointer. Okay. So, okay, stroke here. That's the distance between the fully open and the steady state closed position. That's the stroke, contact stroke. And contact penetration is the distance from the first contact touch of the arcing contact and the steady state closed position. This distance here. Over travel is this part. Some breakers has it, some doesn't have it, so that depends on the design. So that is also something to compare with the reference. Speed calculation point for calculating closing speed and opening speed. So basically it's the average speed between these points that is the speed that you calculate. And that is something that the manufacturer or breaker should specify. However, if there is no such specification, you can always use like the default value, which is contact touch and contact separation for closing and opening respectively. And the lower point is 10 milliseconds before, and for opening that means 10 milliseconds after the upper point. And that will then correspond to arcing zone, more or less. An arcing zone is the zone where the arc is supposed to be extinguished. And after the arcing zone, the damping zone starts to dampen out the force, the energy that you have in the moving contact. So if you don't have a good damping, then it can mechanically hit the stop here and actually be destroyed. So at open you have also an over travel and a rebound. And what I told about rebound before, if this rebound goes longer up, you have a bigger bound here, then it's a risk that the contacts come too close to each other and you get the restrike of the arc. And that is a dangerous condition, because then it will be a standing arc that will cause the breaker to explode. Or at the closed state, you can also have a rebound, meaning that the curve goes down, and if it goes down too much, then you see that it goes below the level of contact touch, and you get a small interruption actually. So that is not good either. Something more here? No, I don't think so in that picture. So a little bit about the standard of breakers, circuit breaker testing. This IEC, this international standard 62271. So these standards are basically made for type test, but it also has sections for maintenance and commissioning and so on. But they're not so well. It's not so much written in those ones. The biggest part is type test and routine test for circuit breaker manufacturers. But however, it's a good reference, and yeah, what does it say about motion measurement? It doesn't really say this. By the way, the section 10 is about commissioning and maintenance and so on. So it refers to section 7, that is the routine test in factory. So, and motion is not, it's not mandatory in the standard, but I think for type test it's mandatory, and it's mandatory to make some kind of reference graph that the manufacturer have in the procedure to test, to do the final test of breakers. So they have a reference graph that they compare with. So here, what does it say here? It says a little bit vague that a record can be made of the mechanical travel characteristics where the circuit breaker has been assembled as a complete circuit breaker for the first time site, and so on. So it's not really mandatory, but it's a very good thing to do to reveal problems in circuit breaker. And if we read what's this section 7, which is for the routine test in the factory, then it says that if the measurement, the routine test then, meaning the routine test, is performed on site, the manufacturer shall state the preferred measuring procedure. So this is important. Oh, sorry. This is important, I think, because this means actually that manufacturers they have a responsibility to do this for customers to explain how to do the motion measurement. So especially for buyers of circuit breakers, they can put requirements on the manufacturer to get reference graphs, to get instructions how to connect transducers and so on. And then they can even refer to this standard and say this is how it says. So that it's important to know. So, and what does it say more here? The mechanical travel characteristics can be recorded directly using a travel transducer or similar device on the circuit breaker contact system, or at another convenient location on the drive. On the drive to the contact system, where there is a direct connection and the representative image of the contact stroke can be achieved. And then it says also that mechanical travel characteristics shall be preferable a continuous curve shown in figure 23. So the 23 is this kind of idealized curve for a, so this is something that, how the standard describes how travel motion is done. So we go on here. So now I will go into more practically how to do this and different methods of travel motion measurement. So different ways to attach the transducer. So one is direct to moving contact, or it's operating rod with linear movement. And this can be done on certain breaker types, not all. For instance, bulk oil breakers, oil minimum breakers, some SF6 dead tank breakers, most vacuum breakers. And second one is direct to moving contact with angular movement. This is a kind of special design of circuit breaker. I have a picture of that I will show later. But the moving contact is actually as a rotating motion. So that one you can measure with the angular movement. Then you can do indirect attachment with linear movement. For example, on operating rod at driving mechanism, and indirect attachment with angular movement. For example, on gear between operating rod and breaker column. I have pictures of all of these I will show. This is the first example. This is a bulk oil breaker with huge tank here filled with oil. Up on the top here, that's where the transducer is connected or attached. And on the top here, there is a small lid you can open, and and you can put a rod in that lid, a threaded rod, and screw that rod directly into the main contact, which is down here. So in this case, you have a direct connection between transducer and main contact. So you see here the enlargement of the transducer, and the rod here going down in this big tank. Next example was with the oil minimum breaker. This is an old medium voltage breaker. So it's the same principle actually, but here there is also a hole here in the top, and you can put the rod down in that hole, and there are threads in the main contact. So this is a one-to-one measurement of the contact motion. Next example, this is the dead tank breaker with indirect linear measurement. So meaning that you use a linear transducer, but it's connected to this rod that actually is doing, it turns, it's a rotary motion on this rod. And you have this lever that forwards the motion to this joint here and makes it from rotary to a linear motion. Next example, it's also a dead tank with indirect linear measurement. So here you cannot see actually what happens but since the main contact is located in this housing and moving in this direction, you can figure out that the linear motion here is not exactly the same. There is some link system in here that you use to measure. Another example, another dead tank breaker. In this case, you use a rotor transducer placed down here to this shaft or axis, and you see here you have operating shafts between that are connected between the phases. So, and this motion is that it's connected to the linear movement of the moving contact, but it's not a direct connection. So, next one. In this case, it's a direct linear measurement because this rod is connected directly to the main contact. It's also a dead tank breaker. Now to a very common drive from ABB, or actually, HMA. And here you actually put the transducer in the driving mechanism. And for certain breakers, like certain SF6 dead tank breakers, the shaft from the operating mechanism goes directly so linear direct measurement. Now on to to indirect angular measurement. You see the transducer here is located. The operating mechanism is here. So from the operating mechanism, you have a rod going from neck into this gear house. So, and if we look at the enlargement here, the rod is actually, yeah, it's coming through this pipe in connecting to this point, and this rod goes to the other phases, phase B and C. And this rod goes down to the opening spring, which is located in this compartment here. And there is also a rod going up to the breaker pull here, to the moving contact. So in this case, you measure the rotary motion to reflect the linear movement in here. So that's an indirect angular measurement. This is also an indirect angular measurement, but in this case, yeah, there are actually two examples. This is the same as on the previous one, but this one is the special operating mechanism from ABB called BLG, where you measure the motion of the closing mechanism. So, and that's an important measurement to measure damping of the closing. So, and this part makes a one turn, 360 degrees for each close operation. So there is a special reference graph for that one also. So that in that case, it's not the measurement on the contact system, it's a measurement on the drive actually. But that's also important. So what are the advantages with direct attachment? Yeah, the measured quantity is the real stroke of the moving contact. Means that you have a one-to-one relationship between the movement of the transducer and the movement of the contact. So there are no conversion factors, tables needed, and so on. And motion is clean, undistorted by gears, mechanical play, or torsion, operating rods, etc. So, and yeah, as a result of that, at a direct attachment, you can also do absolute measurement. That means that 1 millimeter at the transducer corresponds to 1 millimeter at the contact as well. So why don't you do this all the time then? No, because it's not possible for all breaker types. It's the opposite almost. That it's a small part of the installed base of breakers that you can make a direct connection to the main contact on. So, so because there is no access to the breaker chamber, due to that it's under SF6 pressure, or it can be vacuum or whatever, or so on, and or GIS. You know, you cannot reach the moving parts inside. So, and on some breaker types, the type where you have two brakes in one phase, like a T configuration, then there is a small gear also between the two braking chambers at the top. So even if you could measure on the pull rod that you have in the column. It's not exactly the same movement that you have at the contacts. So it's a little bit complex. So see how time is running here. Yeah. So different options of indirect motion measurement. Yeah, the travel in the transducer is a transducer attachment point is recorded as is, linear or angular. This is more now methods in our system, not necessarily how you attach the transducer to. This is how our system can measure in different ways. So this is a good way to use as a footprint or reference to future measurement. So yeah, and stroke velocity and other motion parameters might not be comparable to factor results, but since an own reference is created, preferable at commissioning, this is considered satisfactory. So this is something that yeah, to consider if you don't have instructions or reference values, and so you can always create your own reference and then do the trending to see changes in the behavior, the mechanical behavior of the circuit breaker. So that's with indirect motion. So that meaning that yeah, by yeah, it's implicit that with indirect motion that the motion is not exactly the same as measuring direct at the contact. So that's why your value cannot be compared exactly with the reference values from a manufacturer. And another option is to measure the travel in the transducer attachment point, linear or angular, and then you can convert the travel by means of a conversion table. So that can be one way to kind of to create the correct comparable graph comparable to the factory results. You buy a conversion table, and so you can recreate the real travel motion. And in that case, you can compare all parameters. So here are the different measurement options in our system, measurement system, and I will explain them one by one later. And absolute measurement, the transducer is reference. As I said, that 1 millimeter at the transducer at the contact is 1 millimeter at the transducer, and you can have both angular and linear transducer in this case, and then it will be presented in the same quantity. And the second one, absolute measurement with linear conversion factor. That's the same presentation in distance and angle. Next, absolute measurement with conversion table. in this case, it's only distance as presentation quantity, what you see on screen. So what you actually do is you convert an angular curve to a linear curve or linear movement. Relative measurement. This is interesting. The nominal stroke is reference, and the presentation quantity is only distance, right? Only millimeters, regardless if you're using a rotary or a linear transducer. So now, more explanation for each one of these that I listed. So absolute measurement, the contact movement is equal to the transducer's movement. The transducer has to be thoroughly calibrated as it is the reference for the measurement. That's important. The electrical length or angular span of the transducer is the calibration quantity. So it's independent of the measurement channel's reference voltage. For instance, if you would switch between different instruments like the TM 1700 or an Eagle, which has different reference voltage, you can still use the same transducer calibration. The measurement instrument will establish a scale factor, which can be calculated in this way: transducer's electrical length or angular span divided by the reference voltage. So that scale will have the unit millimeter per volt. So this is perhaps a little bit too much information, but anyway, absolute measurement with linear conversion factor. In this case, you do the measurement according to the absolute method, but in this case, you multiply the scale factor with the conversion factor. And the results are shown in the same quantity as measured. The thing is that, like some breakers, you can have this linear conversion factor. Like you know that 1 millimeter at your transducer corresponds to 2 millimeter at the breaker contact. And there are such types of definitions. And you can also do an angle to distance linear factor, meaning that 1 degree, for instance, corresponds to 1.2 millimeter at the breaker contact. That's also possible. So this is an example of the linear conversion factor. So if you would have a transducer here at this point and your moving contact here, you have the relationship that is between this motion and the contact motion. The relationship is L2 divided by the L1, the length of the arms here. So that's, and the same here, but you have a different link system. This goes up to the main contact, and you have a rod here where that goes to operating mechanism, and on the rod you connect your linear transducer, and provided that the conditions are like written here, you have the same angle here and here, and the relationship between the motions would be a linear one, which is with a factor L2 divided by L1, the length of the levers here. So another example, this is from the real life actually, an old generator breaker called the DB or ABB, where this arm, it's a disconnector arm actually. So this one goes in the circular contact path. and normally you put the transducer here. So in this case, you can calculate the travel in millimeter among this along this circumference of the contact path by using the pi and so on. Yeah, quite simple. This is another example of the rotary movement of the main contact. So this is a Westinghouse breaker called SFA. So it has got 4 brakes actually per phase, and in this compartment up here there are two main contacts, and that's what's shown here. You can see only one of them in this picture, and it's the same on the other side. So, and the movement is a rotary movement. You put the transducer in the middle here, and the whole contact the main contact is making a rotary movement. So it follows this periphery of the circle. Quite interesting. In this case, you need to, it's quite complicated to test this breaker because you need to evacuate the SFX gas. So to be able to attach your transducer here in the middle. And this is basically, I think this is the resistor contact actually, pre-insertion. That hits before, and the main contact is here. You have the resistors here, I guess. Yeah. So time is a little bit short, but I think we will manage it. Absolute measurement with conversion table. Then you use an angular movement, and you measure with a calibrated transducer, and then you convert the angular movement by a conversion table to a distance. So the advantage with this is that the conversion can be unlinear in order to reflect the geometrical transmission function of the breaker cinematic chain. So for example, you can have different factors at different angles. For example, from 0 to 1 degree, that could correspond to 2 millimeters at the contact, while a step from 30 to 31 degree would correspond to 3 millimeters. So for each step, you can have a different conversion factor. So you can basically reflect any kind of transmission graph in that. So this is a common example. It's basically what you had in, let's see here, in this picture. You have your motion transducer here in the middle, and the rod goes up here, up in the column. So that's basically what you saw here. Yeah. So this you understand that where's my pointer? Here. If you put the transducer here, you see that depending on the position here, you will have different movement of the contact. It's basically a sine graph that it follows. So that's why you need an unlinear relationship, a table that compensates for this unlinear relationship. Sorry. Finally here, the relative measurement. which actually is a very good method and quick. It has its advantages, but also some disadvantages. So in this case, the breaker's nominal stroke is used as a reference for the measurement. And I will explain how that works. So in the first recording session, the scale factor is established. And it takes the nominal stroke, which is the stroke that you put in your breaker definition in the software, and divides with the difference in voltage you have between the closed position of the breaker and the open position. And then it established this scale factor, millimeter per volt. And the first recording will be, per definition, it will receive exactly the same stroke as nominal stroke, because that's what you use for your, so to say, calibration. And the scale is maintained throughout the recording session, so you can see changes and fluctuations in stroke. But so this is the advantage. These are the advantages: quick and easy to set up. No need of transducer calibration. You can use an uncalibrated transducer. And no need of transducer selection even. And it doesn't care if it's a linear or a rotary transducer. Both can be used. And it's perfect in most cases to use as a footprint for future comparison and trending analysis. But the disadvantages with the relative method is that it will not reveal incorrect stroke, as it assumes that the nominal stroke is correct. The first recording will always be exactly as the stroke you have put as nominal stroke, regardless if the real stroke is only 50% of that. So that's a disadvantage with this method. And depending on the transducer attachment point and its mechanical relation to the moving contact, then the parameters like motion, related parameters, velocity, penetration, and so on, they will not be exactly as the factory reference values. So that can be explained in this graph. This is actually, like, if you do this example with the transducer here and compare to the movement here. So if you move that wheel, the transducer, now it's 180 degrees, it's too much, but let's say we move it 90 degrees. So you will have this deviation from this. If you would have a conversion table, the motion would be like this, or if you would measure directly on the moving contact. But if you measure with the relative method, it will have the same scale factor throughout the stroke. So in the beginning and the end, of course, you will have the same values, similar at least, but in the middle, you can have some deviation. Now the last slide, I think, and summary methods. So I divided this in attachment, way of attachments mechanically to the breaker. You have direct and indirect attachment of the transducer, and the transducer type, linear and angular, and the applicable methods in our software, and so on. So So for direct attachment, you can use both linear and angular. You can do absolute measurement. And you can do also with factor and conversion table for angular only. And the indirect attachment of transducer, you can use the absolute with factor and relative, of course, and absolute measurement also for angular and factor, absolute with factor and conversion table and relative measurement. So the and examples here you see for the relative, it says footprint here. You can do that both with the linear transducer relative and angular transducer relative. That's made footprint measurements. I didn't mention here, but also some of these other measurement here with indirect connection of transducer. That should also be footprints. If you don't have like a factor that is like specified by the manufacturer or conversion table or so. Okay, I think that was the last slide. So we have a few minutes. I can stay longer if we need also.
Thank you so much, sir, for that wonderful presentation. So
You're
guys, we are now open for any questions that you may have. Please type in the chat box, or you can raise your hand if you want to, then we will unmute you if you have a question. I guess we can give them 1 minute to type in their questions, or 2 minutes. What do you think, sir?
Yeah, sure. Can I see, is there a way to see the questions? Can I see them, or only you?
At the moment, we don't have questions here, sir, but yeah, I can make you to see the questions. Let me check. Yeah. Let me make you as an organizer, and now you will be able to see if they have a question. But for those who are leaving, by the way, don't forget to answer or to fill up the survey that will pop up on your screen. It will really help us in improving our future webinars. And if you have, maybe right now we don't have questions, but in future, if you have questions, you can also send us an email. Niels, by the way, do you have a contact number there or email?
Yeah.
Or you can just send us in Megger Asia. Doesn't matter. We can answer
Yep.
it.
You know my email.
Yeah, I have your email. I
Yeah.
have your email, sir. Oh, I guess we have a question here. Let me see. Yeah, we have a question here, Niels. On the graph, at which movement we can choose the velocity?
On which graph?
We can choose the velocity.
Choose.
Or maybe we can see the velocity.
Okay. I mean, that if I...
Or you want to move to another question here? What is the disadvantage of over travel during closing?
Okay. Yeah, it depends on the design of the circuit breaker. Some circuit breaker doesn't have any over travel, and because of it's impossible because of the design. Some breakers must have over travel to be able to latch in a closed position. Then, yeah, it should show this kind of problem. And yeah, the possible danger with that is that it will break mechanically due to fatigue of the parts. It's constantly hitting some mechanical stop. So about the previous question, we had the graph here. So yeah, the graph here is supposed to show the travel versus time of the contact. So here is the open level we defined as 0 millimeter, and then it goes up to close level. Yeah, so this graph shows a close open operation. It goes open again. And the velocity is usually defined between 2 points on the graph. So that's where you can calculate the velocity. I don't know if that was the answer. Anything more?
Michael?
Hi, sorry, sir. Yep. The other question is there any reference standards or guidelines for acceptable contact and motion travel measurements? Do you have any standards, sir?
No, I mean the standard that I know is the one that I was talking about, the 62227 IEC standard, and which only briefly explains the motion measurement. And it's also, like I said, more it mentioned that you can do it, not that you have to do it. And but I think for type test, or at least I know for manufacturers, they use motion in the development. Of course, they must do that in order to make the design. So yeah, for manufacturers, it's required. For users or customers of the circuit breakers, it's not really required, but it's a good thing to have in your maintenance strategy, and a good means to find faults in the breaker to prevent more danger and major shutdowns.
Okay. Another question here, how to evaluate contact bounces? What is wrong?
What is wrong? It's also hard to say. It depends what you mean. If it's showing a bounce in an electrical bounce or physical bounce, I mean with physical, like a movement bounce, that's two different things. The electrical bounce can be due to, you have the first touch is the arcing contact, when you close the breaker, and the arcing contact is not a very, very good conductor. It can have also, it can be burned a little bit. So, and the purpose of the arcing contact is not really to be a good conductor. It's more when you open the breaker, it should carry the arc and stand the heat of the arc and as well, and so on. But this can cause contact bounces at the closing. You can see perhaps first touch, but then it's bouncing a little bit until the main contact goes in. And after that, there shouldn't be any bounce. And the time, the bouncing time can be then, it depends on the speed and the length of the arcing contact, of course. But as an example, like if you have a 20 millimeter long arcing contact, and let's say you have a closing speed of 3 millimeters per 3 meter per second. That means 3 millimeter per millisecond. That means almost 7 milliseconds then from first touch to main contact, right? So that can be pretty long bouncing time actually. But if you see, it's all about like trending and so. If you see a behavior that you have not seen before on a particular breaker, then you should of course ask what is the reason for this. It can be it can be a loose arcing contact, for instance. That happens also. So that's the electrical bouncing. The mechanical bouncing is what, in this graph. If it goes up here and bounces down below the level of the steady state close position. And this can be different depending on how effective the damping is in the system. You have the same here on the opening part. This rebound here, mechanical rebound. So, and also again, it depends on the design. For instance, this example we have, it goes here. It seems not to change the speed so much in the damping zone. So many breakers, they have, you can see very clearly that at some point here, it's bending. The curve is slowing down. The speed is slowing down, and that's when the damping kicks in. So that also depends on the breaker design, how it should be. But the rebound here, as I said, if the rebound is huge, like it goes up all the way to the to the half of the stroke, then there is a risk of restrike. Since also the gas inside, after an opening, the gas is a little bit ionized. It's a little bit less good isolator, so the risk of restriking is bigger than in this situation. So, but if you have that kind of rebound, there is a serious problem with the breaker. It's more likely that you have that you see a mechanical stop here in the overtravel, which indicates then that the damping is not good. damping is missing, basically. So that's one of the most common problems, I would say, in circuit breakers. Lack of damping, because that's a part that also need to be maintained. It's usually a dashpot filled with oil, and sometimes they are leaking oil and need to be maintained and changed and so on. Okay, I don't know if that was a sufficient answer, but I try.
Okay, sir. Let me just select some few questions that maybe. Is there any advantage of over travel during opening and closing?
Yeah, I mean, advantage. You mean advantage to measure it, or advantage? I don't understand really the question. Advantage to whom? I mean, if you measure the travel curve, you will automatically see the over travel. So there is nothing that you need, nothing special you need to do to obtain that information. Just measure motion and you will see this parameter. And then advantage, I mean, yeah, it's advantage to consider these values and yeah, like compare them to reference graphs or to your footprints or whatever, to see that those parameters doesn't change. So that's another advantage in the analysis. Yeah.
Sorry, I always forget the mute. Okay, another question. What is the reason of contact welding?
Contact. What did you say?
Yeah, what is the reason of contact welding?
Welding.
Maybe, yeah, have you experienced that one, sir, in a circuit breaker?
You mean that contacts are welded
Correct.
together
Yeah.
due to the arc? Oh, no, I have no experience of that, actually. Yeah. So I don't know, but what I can guess, contact welding, yeah, I don't know if that happens on high voltage circuit breakers.
Correct.
On relays, I know it happens, that the contacts are welded together instead of opening. Of course, I mean, it could happen also on bigger breakers, but I have no experience. Anybody else that has experience of that?
In a low voltage, maybe in a miniature relay or.
Yeah, I would say so. Yeah.
We have another long one here. What if the velocity goes down below the acceptable range during closing?
Yeah. That could be different reasons. It could be, like I said here, wrong adjustment or problem with springs, lubrication pressure, etc. So the thing can be also if the speed goes down. Yeah, that's basically if you have some problem in your link system that it sticks in some way. You have corrosion or dried grease or whatever that makes everything to need more force to move. That could be one reason. And you can have a damaged close spring as well. That it could be one reason.
Okay, sir. Sorry. Maybe for the last question, because we're running out of time. The last question I can handle, or we can accommodate, is: does over travel creates problem on below?
Over travel.
Yeah, does over travel creates any problem?
Yeah, I mean it not necessarily, but if you don't watch out, if it's excessive over travel, and if you see, if you would see a flat surface or flat area here on the graph, then you would watch out, because then it would be a sign that something is hitting a stop mechanically. So yes, it can be a problem in that way.
Okay, so there are some questions here asking about the equipment, our equipment, available equipment that can measure these parameters. Can you suggest models for this measurement, sir?
The models, yeah, we can go with the Egel and with also the TM1700 and TM1800.
Yep, and I also sent him a reply that you can check our website, sir, to know the details of those devices. And also we have some previous webinars regarding those models. So if you can visit our website, there is a webinar tab there, and then you can see the topics about the breaker testing, and there are some webinars there that mentions the models that we have. So I guess, in as much as we want to answer, we have a lot of questions, but the time limits us to do so. So I guess that concludes our webinar for today, and I'd like to take this opportunity to thank you, Niels, for your time here in Asia, and hope you can see you again next time for other webinars. And again, thank you guys for attending this webinar, and hope to see you again next time. Please stay tuned, and we will have more webinars in the upcoming months. Thank you, Niels. Thank you, Zoom. Thank you, Grace.
Thank you,
Goodbye,
Niels.
everyone.
Thank you, Michael, for this meeting.
Thank you.
See you again next time. Thank you.
Yeah, see you.